So here we have a plane, and it is being observed by this tower O, right, this radar tower. So we want to find its coordinates in both cylindrical and spherical coordinates. So the first thing we're going to do is we're going to calculate, first we're going to convert this initial velocity into meters per second. So we have 250 kilometers per hour. We divide that by a factor of 3.6 to get our initial velocity in meters per second. So we have 69.4 meters per second. The next thing we want to know is the V after 60 seconds, because we're being asked to find information about this 60 seconds after it takes off. So we have V is equal to V naught plus AT. So this is, we just found V. We just found V naught rather, so that's 69.4 plus 0.8 times 60, which is the time, and 0.8 of course is given to us by the problem. So this will give us 117.4 meters per second. Next we want to find the S after 60 seconds. So we want to find the displacement after 60 seconds. So the displacement is going to be given to us by a kinematic equation. So that's S is equal to S naught plus V naught T plus 1/2 AT squared. So we know that the initial displacement is 0, and we know the rest of this information, so we're just going to plug it in. So this is equal to 69.4 times 60. Sorry, that was a little messy. Let me rewrite that. 69.4 times 60 plus 1/2 0.8 times 60 squared. So that will give us a displacement of 5,610 meters. 1 second, I want to do that. Yeah, that's going to make it a little easier for me to make this neat for you guys. So next we want to find the y coordinate and the associated angle. So essentially what we're looking for here, I'm going to need to do some drawings to illustrate what it is that we're looking for, but we want a y coordinate. So the y coordinate is going to be this distance, right? This distance. And I'm going to draw you guys a diagram real quick to illustrate the theta that I'm talking about here. So we have our plane here, and so this is our r, which we're going to need to calculate our coordinates. This is going to be y, which we're trying to find here. And we have a component VR along the path, along r, right? That's going to tell us how fast this radius is changing. And we have a component VXY. And we have a component V theta, which is tangent to this r. And this is theta, and this down here is also theta. So this one is V theta, right? So we want to find out what this theta is. So we also want to find the y coordinate. So the y coordinate is going to be given to us, of course, by, it's going to be the projected along this line. So we're going to be saying cosine y is equal to the s cosine of 15 degrees, because this is the angle between the s, which this is s, right? So this is the angle s between s and y. So that's going to be 5610, which we found right here, times cosine of 15, which will give us 5420 meters. Now we have that. We can find the theta. The theta is going to be the tangent, the inverse tangent rather, of this distance over this distance. So we have, this is our opposite and this is our adjacent. So we're saying the inverse tangent of our opposite over our adjacent will give us the angle. So this is going to be y, which we just found, that is 5420 over 3000, and that will give us an answer of 61.0 degrees. Now we want to find what r is. So r is equal to the square root of, and this is x, right? This is equal to 3000 because we know this is 3 kilometers. So this is 3000 squared plus 5420 squared. Now this will give us an r value, apologize for this, an r value of 6190 meters. Next we're going to calculate, so now we are finally going to get our coordinates, right? We're going to get vxy, or at least we're going to get one of our coordinates. So let's calculate this. Vxy is going to be equal to v cosine 15. So this is going to be v cosine 15. Why is that? So we have this v along this path, right? So this is going up like this, and the angle between that and v is 15. So if we want to project it along this line, right? If we want to project it along this line, we're going to need to use the angle in between these two. So if this is vxy, right? You can see that. Then this is the angle here. We're going to use the angle in between, so that's 15. So v cosine 15, so vxy is equal to 117.4 times, so this is the initial velocity, this is the velocity found back here. So 117.4 times cosine of 15, so that vxy is equal to 113.4 meters per second. Now we don't need this answer for this part, for part A, but we are going to need this later. So VR, this one is part of the coordinate system that we're supposed to be finding in part A. So that's the same thing as r dot. That's vxy times sine of theta. So it turns out we are using this in this part. So this is going to be extended along this line, right? So if we want to find this guy, we need to, this is also theta. I forgot, I neglected to mention that. No, it can't be. That's not theta. This is going to be 90 minus theta, right? This angle right here. So I could say the cosine of 90 minus theta, or I could just say the sine of theta, which is what I did here. So VR is equal to R naught, which is equal to 113.4 times the sine of 61, which is what we determined theta is. So that's going to give us a R dot of 99.2 meters per second. So this is our one of our answers for part A. So we're going to highlight that. We're going to put that in a box. And I'm going to give myself a little more room here. And I'm going to write that down there so it doesn't go away. So now we have this guy. We want to find next, we want to find v of theta. So v of theta is equal to r times theta dot. And this, of course, is equal to vxy times cosine of theta. And again, this is because this angle between V theta and Vxy is theta. So this is going to be we're going to have r times theta dot is going to be equal to 113.4 times cosine of 61. So our theta dot is going to be equal to 55 meters per second. And then theta dot is then going to be equal to 55 over r, which we found up here is 6190. And so theta dot is equal to 88.88 times 10 to the negative 3 radians per second. So this is another one of our answers for part A. We're asked to find r dot, theta dot, and z dot. So we have found theta dot. Next, we want to find z dot. So z dot, of course, is, so this is the speed at which it's moving upwards, right? Perpendicular to the ground plane. So z dot is going to be equal to vz, which is equal to v sine of 15, because again, v is moving in this direction. This is 15, so this angle up here is also 15. So if we want to find the component of it facing upwards, we're going to multiply it by sine 15. So that's going to be 117.4 times sine of 15 degrees. So z dot is going to be 30.4 meters per second. Let me write that a little more clearly for you guys. So that is going to be equal to 30.4 meters per second. So there we have successfully answered the first part. So we're done part A. Now you'll notice that I've already gotten further than Professor Nabakti has. I'm going to continue into part B. So for part B, we're going to draw a new diagram. So just like I drew the top-down diagram showing V naught, V theta, Vxy, and Vr, I'm going to draw a new diagram that is going to show, so basically for the spherical coordinates, we want to look at this triangle, and we want to see how is Vr moving away from the center as if this was a sphere, right? So if this is a point on a sphere, this is going to be given to us by this r dot, which is going to be moving away from it, and it's going to be giving us the rate of change of phi and theta. So to do this, we're going to need to draw this again. So our plane is, and basically I'm just drawing that triangle from on there. So our plane is out here, and it has a, so this is going to be the z direction, and this is going to be the r direction. So this is going to be, we're going to have a Vr in this direction, so that's equal to r dot, which we're supposed to find. We're going to have, so if the theta is moving like this, right? Imagine something coming out of the page. So this is theta. So this is going to be theta. Yeah, I'm gonna have to draw this in 3 dimensions, unfortunately. So this is going to be perpendicular. This is going to be our okay, we'll get to that in a second. But first we're going to look at z. So we have z. This is the z distance. Obviously, this is z. Z is going to be equal to y, which we found previously, times tan of 15. So if we look at this right here, we're going to say that the z distance is going to be the tangent of y times 15. You guys, that's some basic geometry. So z is equal to 5420 times tangent of 15, and that means that z is equal to 1451 meters. Now we have to find out what phi is. So phi is this angle right here. So phi is going to be equal to the inverse tangent of z over r. So this is our r. This is going to be z over r. So that means that phi is going to be equal to the inverse tangent of z, which we just found. So that's 1451 over r, which we found right here, 6190. And this will give us a phi of 13.19. Next, we want to find our theta dot. No, we don't want to find our theta dot. We want to find our big R. So our big R Okay, so before this is the R we were finding, but this is the big R, so I got a little confused there. This is big R, down here is little r. So that's why we use this equation to find phi. But now we want big R. So big R is going to be equal to the square root of r squared plus z squared. This is going to be the square root of 6190 squared plus 1451 squared, which is 6360 meters. And now we're going to say that VR is equal to R dot, which is, okay, so this is where the hard part comes in. So we got this, we're going to draw this up here. So we want to say that this is phi. And we know this guy, right? This is VZ. And we know this guy going out. These were given to us before. So this guy is VR and this guy is VZ. So we want to find the components of VZ along this line. So we want to do that by saying VZ times the sine of phi, because this is, phi is down here, right? So this is the sine of phi, plus VR times cosine of phi. And that should give us the components of both of these guys along this line, right? Along the center line between the plane and the point, the origin. So this is going to be, R dot is going to be equal to VZ, which is 99.2 times, okay, I got this backwards. VZ, which is 30.4 times, yes, which is right here, right? Times sine of 13.19 plus VR, which we found above, which was right here, 99.2 meters per second, times cosine of 13.19, and that will give us an R dot of 103. My equal signs are looking so bad today. 103.6 meters per second. So that is one of the answers we have to find. The next, I'm going to give myself a little more space here. So the next thing we have to find is our theta dot. So what is theta dot? So theta dot we found before. That's great. We don't have to answer this part again. We have 88.88 times 10 to the negative 3 radians per second. That's wonderful. We can box that. And next we want to find phi dot. So we don't know what phi dot is, but luckily we have this equation, which is v phi times r of phi dot. These two are equal to each other. So we can say that this is equal to, and now we're doing the exact same thing we did before, but a little different. So this one is going to have a component. It's not going to be a component, but it's going to have something perpendicular to it, right? So this is a 90-degree angle. And this is going to be our v of phi. This is the rate at which this guy is changing. So this is going to be given to us by it's going to be a similar method to what we did before, but these guys are going to be flipped now. So this is obviously pointing in the opposite direction than this, so that's going to be being subtracted. So let's look at this guy first. We still have a component of this being projected along this line. And the angle is now going to be sine of this angle right here, because if this angle is 90 minus phi, so we can just say that to project that line along this one, we just need to say the sine of phi. So now we have v r sine of phi minus this component, which is going to be pointing in the opposite direction if we were to project it, right? So minus vz cosine of phi. So this is going to give us, again, 99.2. Okay, sorry about that. That's not right. Okay, I got something wrong because the phi is going to be increasing, right? It's going to be actually going up because this, if you think about this plane going in this direction, this phi is just going to be getting higher, right? So I'm actually trying to find v of phi projected along this line right here. So if I want to find v of phi along that line right there, we're going to have this, we can use the same technique I was just talking about before, but it's going to be flipped. So now we're going to have this guy is going to be positive and this guy is going to be negative. And the idea that you guys have to keep in your mind is that we are projecting along certain lines to give us the coordinates. We're trying to find the components of what we already know along this line, so we can use this information. So now we have Vz cosine theta. So Vz we know is 30.4 cosine of 13, and that's not theta, that's phi, sorry, I misspoke. So that's 13.19 minus Vr, which is 99.2 times cosine of 13.19, and this should give us 6.95 meters per second. So if this is what r phi dot is equal to, then phi dot is going to be equal to 6.95 over r, which is 6360, big R that is, and we found that right here. So that is going to give us 1.093 times 10 to the negative 3 radians per second. And there you have it, guys. This is how you do sample problem 212. Now, I have completed this in less time than Professor Nabhakdi did, and I have completed both parts of the problem correctly as shown by the textbook. Obviously, I haven't done it perhaps as well as a professor would have. I'm still kind of messy, but notice that it's not all condensed to one region. It's spread out. There is a clear delineation between where the visuals are and where the math is taking place. It's not all being done on one image. It's not all being done on one slide. I am actually following the method laid out by the book. Now, obviously, I would have to stop for questions, so that would have added a little bit of time. But the difference between, at least in my opinion, between this presentation and his is night and day.